morning, everyone. I would like to tell you that I appreciate your interest in this topic. I will present Apache Druid auto scale out and scale in for streaming data ingestion on Kubernetes. Let me introduce myself. I am a DevOps engineer and also senior software developer at SK Telecom. That is Korea's #1 telecommunication provider. My role is Scrum Master for cloud platform development using Kubernetes, Docker, and a variety of applications. I have been a committer of Apache Impala project since last year. Before joining the current company, I had worked at SAP Reps Korea for about 9 years. My role was a senior software developer for SAP HANA in-memory engine. I had designed and written server-side code by using C++, and I had been involved in SQL script parser, semantic analyzer, SQL optimizer, rule and cost-based optimization, plan explanation and executor, SQL plan cache, and SQL script debugger. I list up the items for today's agenda. First of all, in the motivation section, I want to talk about that I encountered issues and how I solved them when we adopted Apache Druid as a streaming data processing engine. Secondly, in the background and terminology section, I'm going to briefly explain important architectures and key terminologies to help you who are not familiar with them understand Druid, Kubernetes, and relevant things. Thirdly, we are going to compare the current approach of autoscaling in Druid with an alternative way on Kubernetes using horizontal path autoscaling. Firstly, I'm looking into an issue of scaling and workarounds. Lastly, I want to talk about the conclusion. Why do we need autoscaling? I believe the most benefit comes from cost saving by providing resource management. For example, a variety of engines keep intermediate and frequently accessing data into its main memory because the data can be used a lot or soon. Such in-memory data is similar to logical cache. It should have the advantage to process an incoming task rapidly. Supposing many replicas are running on the scale-out landscape, some of them should be ready, but the others can be terminated. This is because of overused resource, especially memory, when the state of the replicas is idle. Therefore, a container management framework such as Kubernetes will enable to manage the number of replicas automatically. What kinds of information do we need for autoscaling? It depends on the characteristic of your target, which will be scaled. For example, a web server generally relies on hardware resource metrics such as the percentage of CPU utilization and proportion of memory usage. However, Apache Druid is suitable to exploit custom metrics from the Druid servers. The custom metrics consist of the number of pending job tasks, the number of idle workers, and other properties. Let me deal with more details in the remaining part. We are going to look at the drawbacks in autoscaling features on Apache Druid. Now let's focus on what I mainly present today. Apache Druid supports autoscaling feature for data ingestion. However, I realized that there are 3 shortcomings. I also figured out that Kubernetes and HPA were able to fundamentally solve them. Let's look into 3 issues. First of all, Druid's autoscaling is only available in AWS. What I mean is that my company did not rely on the feature because we had to use our own premises. Besides, we also have a plan to provide our solution on public clouds, such as AWS, Azure, and GKE. But the feature is not possible on other public clouds except for AWS. By the way, Kubernetes supports autoscale feature. Most public clouds have been providing managed Kubernetes. Moreover, you can set up your own private Kubernetes system on your premises. Second, a few minutes for startup and shutdown on VMs. What I mean is that AWS EC2 is an instance of virtual machine, so the startup is much slower than Docker container. For the virtual machine, a few minutes are required for startup and termination. However, Docker-based container is very lightweight, so it requires a few seconds. Third, Druid autoscaling is tightly coupled with AWS API. This is because Druid engine code exploits AWS API. Our scale-out in algorithm is logically equal to Druid's autoscaling approach, but we decoupled the dependency because Kubernetes communicates with one of the dispatcher node, such as overload node, using REST API. For these three reasons, those are because we make use of Kubernetes. I strongly believe that this way is more outstanding than current approach of Druid autoscaling. Let's start background and terminology section. Apache Kafka is fast, scalable, durable, and fault-tolerant publish-subscribe messaging system. And Kafka is well known for its high throughput, reliability, and replication. Kafka works well in combination with Apache Druid for real-time analysis and rendering of streaming data. SK Telecom adopts Kafka that is used to collect and buffer the events that are then ingested by Druid. It is the reason why we need Kafka that purges the data and act as a buffer when bursts of events occurs. That happens when there is, for example, sensor data from the telecommunications equipment and relevant facilities. Druid is an open source distributed data store. Druid's core design combines ideas from OLAP or analytic databases, time series database, and search systems to create an unified system for operational analytics. Druid merges key characteristics of each of three systems into its ingestion layer, storage format, calling layer, and core architecture. Druid is high-performance, column-oriented distributed data store. It allows us to explore events immediately after they occur and ingest data in streaming or batches. Here is an overall architecture of Druid. Druid can be thought of as a disassembled database. Each core process, such as ingestion, calling, and coordination in Druid, can be separated or jointly deployed on commodity hardware. Today's topic is focused on streaming data ingestion. Overload nodes and middle manager nodes are very relevant to the ingestion. Middle manager generates segments periodically, and the segments are moved into deep storage, which can be HDFS, Amazon S3, and Azure Blob Storage. Let me explain ingestion briefly. Druid supports both streaming and batch ingestion. Druid connects to a source of raw data, typically a message bus such as Apache Kafka, which is for streaming data rows, or distributed files such as HDF, which is for batch data row. Druid converts raw data stored in a source to a more read-optimized format, which is called segment. In Druid, the convert process is called indexing. Let me explain how data is stored in Druid. Like many analytic data stores, Druid stores data in columns depending on the type of column such as string, number, timestamp, and different compression and encoding methods are applied. Druid also builds different types of indexes based on column type. Similar to such systems, Druid builds inverted indexes for string columns for fast search and filter. Similar to time series database, Druid intelligently partitions data by time to enable fast time-oriented queries. Unlike many traditional systems, Druid can optionally pre-aggregate data as it is ingested. This pre-aggregation step is known as roll-up and can lead to dramatic storage savings. In this slide, I want to talk about terminology of Druid ingestion by top-down manner. Three kinds of Druid nodes are involved in the ingestion. When a new task is incoming, Overload assigns the ingestion task to middle manager. Overload is a controller of data ingestion into Druid and watches over middle managers. It also coordinates segment publishing. Middle manager process handle ingestion of new data into the cluster and reads external data source and publish new Druid segments. Middle manager is called worker node. It executes submitted tasks by forwarding them to peons that runs in separate JVMs. A peon runs a single task in a single JVM, and the peon is managed by middle manager. Docker is an open source software platform to create, deploy, and manage virtual application container on a common operating system. What has Docker done for us? It provides continuous delivery. It means we can deliver software more often and with less errors. Also, there is no time spent on DevOps handoffs. It helps security improvement and run anything, anywhere. It promised reproducibility. Containers sit on top of a physical server and its host OS. Each container shares the host OS kernel and usually the binaries and libraries too. Shared components are read-only. Sharing OS resources such as libraries significantly reduces the need to reduce the operating system code, and means that server can run multiple workloads with a single operating system installation. Containers are thus exceptionally light. They are only megabyte in size and take just seconds to start. In contrast, VMs take minutes to run and on order of magnitude larger than an equivalent container. Kubernetes is an open source system for automating deployment, scaling, and management of containerized applications. Kubernetes improves reliability. What I mean is that it continuously monitors and manages your containers. It also scales your application to handle change in load. It provides a better use of infrastructure resources. It helps reduce infrastructure requirements by gracefully scaling up and down your entire platform. It coordinates what containers run where and when across your system. Let's see the relationship between Kubernetes and Docker. Kubernetes is a container orchestration system for Docker container. It works around the concept of pod, which are scheduling unit in the Kubernetes ecosystem, and they are distributed among nodes to provide high availability. One can easily run a Docker build on a Kubernetes cluster, but Kubernetes itself is not a complete solution, and it means to include custom plugins. Therefore, Kubernetes and Docker are both fundamentally different technologies, but they work very well together, and both facilitates the management and deployment of containers in a distributed architecture. Helm is a tool for managing Kubernetes charts are packages of pre-configured Kubernetes resources. Helm is a tool that streamlines installing and managing Kubernetes applications. I think its concept is similar to Homebrew or Yum. Helm consists of two parts. First, Helm client, and second, Tela server. They communicate with each other using Google RPC. Tela runs inside of Kubernetes cluster and manages release of chart version control. It means a new chart can be deployed by rolling update or rollback from the latest deployment. Here is a snapshot of Druid Helm chart in our repository. By the way, I have recognized that, or good news, that Druid Helm chart has been included into the repository of the official Kubernetes Helm chart. Let's see how autoscaling does work internally in Druid. I have copied the description of autoscaling in Druid from the official website. Currently, Druid supports autoscaling by itself. The article says that the autoscaling mechanisms currently in place are tightly coupled with deployment infrastructure, but the framework should be in place for other implementations. This is what I pointed in the motivation section. This code shows the implementation of autoscaling in Druid. EC2 autoscaler was implemented using AWS EC2 API. EC2 autoscaler consists of two functionalities. The first one is provision method, which deploys a middle manager on an EC2 instance. The other is a terminate method, which destroys EC2 instances by providing string list parameters. Now we realize where autoscaling mechanism is placed in Druid engine code. It also means the scaling algorithm and the relevant functions are tightly coupled with Druid engine code. If a DevOps engineer wants to improve or revise the scaling algorithm, the engineer should edit Java code and recompile it. I believe there will be a conflict between Druid core developer and DevOps engineer. Who is the right person to have the ownership of this code? In my opinion, DevOps engineer should have the ownership because Druid is only just one of the application on the big data platform. Let me show how I replace it with independent program later. Let's back to the article. The article says that in our one deployment, middle manager nodes are Amazon EC2 nodes. It means a middle manager process can be mapped to one EC2 node. Currently, the autoscaling is only available in EC2. You cannot use the feature on other public or private clouds by default, so you may implement your own autoscaler code to scale up and down. In the second paragraph of the article, it says if autoscaling is enabled, new middle managers may be added when a task has been in pending state for too long. Middle managers may be terminated if they have not run any tasks for a period of time. So to speak, the logic of scale up and down is very intuitive and simple. Let's jump into how we implement autoscaling on Kubernetes. I'm going to explain how we use Kubernetes and its horizontal path autoscaler with custom metrics. In Kubernetes, autoscaling is an approach to automatically scale up or down workloads based on resource usage or custom metrics. Kubernetes autoscaling has two dimensions. First, the cluster autoscaler deals with node scaling operations. Second, HPA automatically scales the number of pods in a deployment or replica set. The cluster autoscaler scaling together with HPA can be used to dynamically adjust the computing power as well as the level of parallelism that your system needs to meet SLAs. HPA feature was first introduced in Kubernetes V version 1.1 and has evolved a lot since then. Version 1 of the HPA scaled parts based on observed CPU utilization and later on based on memory usage. In Kubernetes version 1.6, a new API custom metrics API was introduced that enables HPA access to arbitrary metrics, and Kubernetes version 1.7 introduced the aggregation layer that allowed third-party applications to extend the Kubernetes API by registering themselves as API add-ons. The custom metrics API, along with the aggregation layer, made it possible for monitoring systems like Prometheus to expose application-specific metrics to the HPA controller. HPA is implemented as a control loop that periodically queries the resource metrics API for core metrics like CPU or memory, and the custom metrics API for application-specific metrics. In order to scale based on custom metrics, we need to have two components. One component that collects metrics from Druid and stores them the Prometheus time series database, and a second component that extends the Kubernetes custom metric API with the metrics supplied by the collect, the Prometheus adapter. As you can see, a yellow box means a container in a pod. Middle manager pod contains two containers. The first one is for middle manager process, and the other is for overload watcher application, which is to expose custom metrics to Prometheus. HPA checks the custom metrics regularly and determines the number of replicas. The value of replicas affects the number of middle manager pods. Here is our implementation for overload watcher application using Python with the Prometheus client library. Let me explain Prometheus client library briefly. If we want to monitor states or metrics on an application, we need to add instrumentation or change value via the Prometheus client library. We can define and expose internal metrics through HTTP endpoint on our application's instance. The Prometheus client libraries offer 4 core metric types: counter, gauge, histogram, and summary. In our application, we are using a gauge metric type only. Gauge represents a single numeric value that can arbitrarily go up and down. It is typically used for measured values like temperatures, but also count that can be go up and down, like that number of running or pending tasks in overload. We define and declare the custom metric to expose them and collect the information of metrics by using REST API from HTTP endpoint in overload process. The unit of all the properties is integer type. Let me explain each property one by one. First one, Druid ingestion number of peons means the number of peons for each worker. As you know, worker is an alias of middle manager. Druid ingestion non-peon is Druid worker capacity, which is defined at middle manager process configuration. Next, Druid worker capacity means maximum number of tasks the middle manager can accept. Its default value is the number of CPU cores. We assume that some peons exist in each worker. Druid ingestion num workers means the number of workers in indexing service. Indexing service is provided by overload process. Druid ingestion num pending tasks means the number of pending tasks in indexing service. Druid ingestion num running tasks means the number of running tasks in indexing service. Druid ingestion expected num workers means the number of expected workers in indexing service. And Druid ingestion current load means percentage of current load. Here is an example to understand how the exposed custom metrics are used in HPA. This shows how scale out does work. There are two tables. The above table is for calculated values using the metrics from overload process. The below table is for collected metrics from overload process. Let's see the below table. We assume the number of peons is 8 because we set the value on Druid worker, capacity of middle manager, configurations, and a single middle manager is running as startup. Two tasks are incoming and overload assign the tasks to a proper middle manager. Now total running tasks are 2 and then 12 tasks are incoming again. A middle manager can have only 8 peons and the remaining tasks are in pending state. In the above table, expected num task is 14, so expected num workers is 2. Therefore, the current load is increased from 100% to 200%. HPA can increase replicas if current load is greater than 100%. HPA can also decrease replicas if current load is less than 100%, and there is nothing happens if the load is equal to 100%. So 200% is a signal to increase replicas. The number of middle manager is 2. 2 workers can cover all the tasks, so current load is 100%. At this moment, there is no change of the number of replicas. New big incoming task arrived and current load is changed to 300%, 150%, 350%, 175%, and so on. As you can see, current load is greater than 100%. So the num workers line in the graph show a trend of increment. By the way, increase of num workers cannot happen in the blue rectangle if it reaches max replicas. Max replicas and min replicas are described in HPA's resource manifest in Kubernetes. Now let's exploring middle manager autoscaling based on custom metrics. The following deployments happen on CLI. The combined shell commands create two namespaces, monitoring and demo. Monitoring is a dedicated namespace for Prometheus and relevant components such as Kubernetes custom metric API with Prometheus adapter. Druid pods will be deployed in demo namespace. Two namespaces are created. As I introduced before, Helm is a tool for managing Kubernetes charts. Charts are packaging of pre-configured Kubernetes resources. We will deploy Druid application using the command. Let's check pod in demo namespace to find out state of Druid application. There are 5 pods: broker, coordinator, historical, middle manager, overload. You may figure out the naming rule of middle manager is a little bit different to others. We assume middle manager should be stateless, but the others can be either stateful or stateless. Stateless application does not require persistent storage. Middle manager actually requires a disk to keep temporal state segment for a while. The temporal segments can be removed when the delivery of segment to the deep storage is done. Middle manager is suitable for deployment controller, which extends replicates controller. So middle manager can be scaled up and down easily. The other pods are now stateful, but some of them can be stateless. By the way, historical should be stateful because it contains segment cache, and existence of the cache is very important for query performance. The cache is the persistent storage. Deployment workload has a suffix of unique ID. Stateful workload has a sequence number which starts and at 0. In the ready column, middle manager has only 2 containers. As I told before, this pod consists of middle manager container and overload watcher container. Let's check out K-pares from HPA. This repo was initially forked from Stepan Prodan's repository. In my repo, I added Kubernetes manifest for middle manager and helper shell script here. Now we move to the local repo. Deploy Prometheus version 2 in the monitoring namespace. Now Prometheus is deployed on the monitoring namespace. The build command generates the TLS certificate which needed by Prometheus adapter. Certificates are successfully generated and the content of the certificate is copied into the manifest file. Let's deploy the Prometheus custom metrics API adapter. Custom metric API deployment and service are deployed. Let's check pod state in the monitoring namespace. Custom metrics and Prometheus pods are fine. Here is row level query to Kubernetes to see the list of the custom metrics provided by Prometheus. Here is the result, which is JSON format. We will deploy HPA controller to scale up and down of middle manager pod. It watches Druid ingestion current load. HPA expects 100 as the target average value. As I mentioned before, HPA can increase replicas if current load is greater than 100%. HPA can also decrease replicas if current load is less than 100%. And there is nothing happen if the load is equal to 100%. Deployment is done. Let's check state of HPA in the demo namespace. HPA is watching Druid ingestion current load custom metric. Target column shows 100 per 100. Min pod is 1, max pod is 16, and current replicas is 1. Now new tasks are incoming in the background. We realize that the change of the target columns and the replicas is increased from 1 to 8. Check HPA state again. Finally, the number of replicas reaches max pod. Let's send a query to Kubernetes to get the current load. Kubernetes API server returns the value. The number of middle manager pod is 16. Let's talk about scale-in issue and workarounds when I applied horizontal pod autoscaling. When horizontal autopod autoscaler triggers scale down for pods, it chooses some victims by its internal logic. The logic has a precedence rules to select a victim. Let me explain the precedence in the remaining slide. By the way, I have not found a way to tell preferred victims to Kubernetes when these pods are running and ready. This is because why I use random fashion. Therefore, one of our running pods will be kicked out and it can be affect the performance. First of all, if the pods are replicas of web server which returns a response swiftly, thus this eviction policy is very suitable to web server. Secondly, however, Druid middle manager is controversial to web server because randomly selected victim can make the worst choice. As you know, middle manager handles ingestion of new data into the cluster. It reads external data source and publishes new Druid segments. This operation should be time-consuming. There are two snapshots that shows pod status. Let's see the second picture. A pink box indicates a pod, and the box can be filled with color, which means the progress of the ingestion task. The second and the first pod may be idle or just started. The third pod will be finished soon, its job. If HPA decides to evict a pod which has been processing data for a long time and will finish the task soon, so to speak, the third pod it should be a worst decision. Thus, the pod which are processing data, their job tasks should be excluded from the victim candidate. Okay, how do we do this? Unfortunately, there is a challenge. Let's see this feature request, which has been an open issue and under discussion for 2 years. The request is about the scale down a deployment by removing specific pods. When I followed up this thread, I felt Kubernetes maintainer seemed not to agree on the necessity of this request. Why? The management of a specific pod is not conceptually suitable with deployment or replica set. Currently, HPA scales the pods of deployment, replica set, and stateful set. In this discussion, one of the contributors suggested the use of stateful set instead of deployment because conceptually deployment and replica set cannot be bound to any specific pod. They were originally designed for that specified number of pod replicas are running at any given time. Thus, management of a specific pod is not conceptually suitable with deployment or replica set. Do we solve this issue by stateful set? Unfortunately, I don't think so. Like a deployment, a stateful set can manage pods that are based on a identically container spec. Unlike a deployment, a stateful set maintains a sticky identity for each of their pods. Now you might feel stateful set could solve the problem, but sadly, it's not available because stateful set has a special property, guarantees about the ordering and uniqueness of the pods. This is called as ordered ready pod management. It means that when pods are being deployed, they are created sequentially in order from 0 to n-1. The termination of pod is performed by backward manner. By the way, we should delete a pod in the middle of pod, but it cannot be applicable in stateful set because stateful set should guarantee two constraints. The first constraint is before a scaling operation is applied to a pod, all of its predecessors must be running and ready. The other constraint is when a pod is terminated, all of its successors must be completed and shut down. By the way, you might guess that parallel pod management can solve the issue instead of order-ready pod management, but parallel pod management also does not delete only in the middle of pod. As I mentioned, replica set and deployment cannot be bound to any specific pod. It means HPA cannot rely on the custom metric information when choosing specific pods as victims. Now we need to understand how replica set manages each pod because there is any possible workaround. The precedence rules are used when deleting pods. Please refer to the source code if you are interested in the rules. The first has topmost priority. When I see the third rule, I can figure out how I can avoid the problem. Let's imagine that all the pods are already assigned and running. We can check middle manager's status in the pod. If it is idle status, we can change the pod readiness status to not ready. Eventually, this is a signal to be selected as a victim. I think this approach can be a workaround. Finally, we have overcome the challenge. Who is the better controller for Druid autoscaling? I think there are pros and cons. I think there is a disadvantage when deploying Kubernetes. What I mean is that autoscaling on Kubernetes can be overkill if you don't have Kubernetes system or it is not easy for you to operate the system. But if you are familiar with any kind of orchestration tool like Kubernetes, you may have got many benefits on this table. Let's see. First of all, Kubernetes can have more wider coverage than Druid. Most of public clouds supports managed Kubernetes, or you can build your own Kubernetes system if you have bare metal infrastructure. Secondly, Kubernetes deploys containers which are rapidly faster than VMs. Start or stop instance of a container takes a few seconds only, but a VMs-based instance may take a few minutes. Thirdly, what do you think about the decoupling? Do you think it is necessary or not necessary? In my opinion, I think this is very important for the sustainable maintenance. Before the decoupling, the ownership of autoscaling is overlapped between Druid engine developer and DevOps engineer. I am sure the decoupling brings some benefits to us. The first advantage is a DevOps engineer can have ownership completely, so the engineer can edit, test, and deploy of autoscaling algorithm, and the determination of the policy is more flexible and speedy than before. Also, regarding the viewpoint of code and library compaction, the embedded code of autoscaler in Druid and AWS API libraries can be completely removed from Druid. Lastly, we have better extensibility. Kubernetes already has lots of features to orchestrate applications. Actually, Druid Middle Manager is just one of them. It is not difficult to adapt autoscaling of Druid historical node into Kubernetes. For these 4 reasons, I strongly believe that autoscaling in Kubernetes is mostly prominent compared with the feature of Apache Druid autoscaling. I really appreciate your listening. Thank you.